Welcome dear students, we are on the CEC Gurukul lecture and we are in the series of quantum technology and we are discussing the quantum sensors. In this quantum sensor, we discuss the atomic clock. What is this atomic clock? This atomic clock can measure time by monitoring the resonant frequency of the atom. This is different from the ordinary clock. So, this atomic clock is a clock that measures time by monitoring the resonant frequency of the atoms. So, it is based on the fact that the atoms have quantized energy levels and transitions between the such levels that are driven by the very specific frequency of electromagnetic radiations. So this clock will measure the resonant frequency of atom by measuring the transition and absorption in the specific quantized energy levels. So this is the this is one of the type of the quantum clock. So quantum clock at first sight atomic clock. So this is the atomic clock that qubits with the transitions so insensitive that their level splitting can be regarded as absolute and serve as a frequency reference and do not seems to quality as quantum sensors. So, but the qubits with the transitions are insensitive, that their level splitting can be regarded as the absolute and serve as a frequency reference. So, their operation as a clock, however, employs identical protocol as the operation of the quantum sensor. So, in order to repeatedly compare the qubits transitions to the frequency of the unstable local oscillators and subsequently lock the latter to the former. So, an atomic clock can be equally regarded as a quantum sensor, measuring and stabilizing the phase drift of a local oscillator. So, vice versa, a quantum sensor discussed previously can be regarded as a clock that operates in purpose on a bed environment sensitive clock transitions in order to measure the external field. External field may be the electric or the magnetic. So, a clock is simply an apparatus that counts a repetitive events, that is in a mechanical clock. A pendulum might swing once every second and by counting the number of the swings and one knows how many seconds have passed. So, atomic clocks use atoms, more precisely the electronic transitions from one state to the another as their pendulum. So, in the atomic clocks we are just taking the electronic transitions from one state to the another state. So, they take advantage of the fact that all the atoms of a particular element have the same electron configuration. So, that is why this atomic clock is used. So, what particular atom? Like cesium and rubidium. So, again I can repeat that this atomic clock has an advantage of the fact that all the atoms of a particular element have the same electron configuration and that can be measured through the atomic sensor, that through the atomic clock. So, different atomic clocks using the same element thus use the same pendulum, unlike for example different mechanical clocks which can deploy a slightly different pendulum due to inaccuracy in the manufacturing processes. But this phenomena serve as the basis for the SI definition of the second. So, the second symbol S, SI unit of the time, it is defined by taking the fixed numerical value of the cesium frequency, that is del nu Cs, the unperturbed ground state hyperfine transition frequency of the cesium 133 atoms to be 9192631770 which expressed in the unit hertz, which is equal to the inverse of the second. So, for this reason the second is actually defined as exactly by this value which is the cycle of a cesium atomic clock, that is 91926317770. So, simplified block diagram of the typically commercial cesium beam frequency reference. Here we are having a various parts and then we can measure the time period. So, today best atomic clocks are so accurate that they would go wrong less than a second if they were tuned on the birth of the universe, that is 13.8 billion years ago. So, we cannot measure anything more precisely than the time. So, an atomic clock work principle is just use the various states. So, how it work? So, this is the work principle of the atomic clock, where the electrons moving around an atomic nucleus can only occupy a small number of the well defined states which have well defined energies. So, one of the key discoveries that led to the formulation of quantum mechanics. So, in the simple Bohr model, it can be imagined that electrons can only move in a small number of trajectories around the nucleus. So, unlike the planet in the solar system, which is principle can rotate around the central star at any distance. So, in an atomic clock, light of a certain frequency, that is generally the electromagnetic radiation, is shown on a atom, or that will be commonly a cooling cloud of the atom. So, what actually here, what are you having? We are having a certain frequency that will fall upon the atom, which is a cloud of atom. If the frequency of the light is just right, the atom absorbs a photon and charge and changes into an excited state. That is the condition when the particular frequency light fall upon a atoms, then it will absorb, then it will change its state. So, the energy of the photons is exactly equal to the energy difference between the two states. As we just take in the case of the laser, the difference between the two state must be equal to the light fall upon it, the frequency energy of the photons. So, in an atomic cloud, this process is repeated repeatedly. So, the efficiency of exciting the atom is constantly monitored and the frequency of the light is constantly corrected to yield the highest efficiency. So, as the atom absorbs from lower state to the higher state, so this efficiency of exciting of the atoms is constantly monitored, and the frequency of the light is constantly corrected to yield the highest efficiency. So, atoms thus constantly watch over the frequency of the light source, which is in turn can be counted and used to measure the duration of an event. That is the purpose of the atomic clock. So, strictly speaking, the energy difference between the ground state and the excited state is constant only for the individual completely isolated atoms. So, external influence such as electromagnetic field can influence the energy levels of the states and thus also the transition frequency. Whenever just we give the another electromagnetic field, then the energy levels will be different and there will be the difference between the one state and another state will change. Thus, this transition frequency will change and that will affect the transition frequency. So, external influences can affect the states as well as its transition frequency. So, atomic clocks are therefore shielded at great expense and special pair of the electric configurations are selected that are as insensitive as possible to the external influence. So whenever we do the performing the experiment, so we have to keep the fix. So the shielded at the great expense, that special pair of the electric configurations are selected for the count and for the absorption count or for the emission count. So it will be possibly make insensitive towards the external interference. So how does a practical cesium atom works? Basically, atomic clock are of many types, but here we discuss the practical cesium atomic clock work. So atoms have characteristics oscillation frequency. Perhaps the most similar frequency is the orange glow from the sodium in the table we are having. So it is the sprinkle, so it is sprinkled on the flame. Now here when we just sprinkle the table salt on which is from the sodium, then an atom will have many frequency, some at radio wavelength, some in the visible spectrum, and some in between the radio and the visible. So cesium 133 is the element which is the most commonly chosen for the atomic clock. So whenever we do the experiment, so just we check the frequency by the orange glow from the sodium in the table salt when it fall upon the fire. So here what we are having, then an atom will have many frequency, some at the radio wavelength and some in the visible range. So and some are in the range of both. So 133 is element most commonly chosen for the atomic clock. So to turn the cesium atomic resonance into a atomic clock, it is necessary to measure the one of its transition or the resonant frequency accurately. Whenever we are converting the cesium atomic resonance into the atomic clock, then there is a requirement to measure the one of its transition or the resonant frequency accurately. So this is normally done by locking a crystal oscillator to the principal microwave resonance of the cesium atom. So this signal is in the microwave range of the radio spectrum and just happens to be at the same sort of frequency as direct broadcast satellite signals. So engineers understand how to build the equipment in this area of the spectrum in great detail. So to create a clock, cesium is first heated so that atoms boil off and pass down a tube maintained at a high vacuum. So how we create a cesium clock? So any atomic clock we will just construct it or instrument it. So first a cesium is first heated so that atoms boil off and pass down a tube maintaining at a high vacuum. First they pass through a magnetic field that selects the atoms of the right energy state. Then they pass through the intense microwave field. After that, the frequency of the microwave energy sweeps backward and the forward within a narrow range of the frequencies, so that at the some point in each cycle it crosses the frequency of exactly 9192631770 Hertz, or we can say cycle per second. So atomic clock's unit is the cycle per second or the Hertz. So frequency of the microwave energy that can be measured. So the range of the microwave generator is already close to this exact frequency as it comes from an accurate crystal oscillation. So when the cesium atom receives the microwave energy at exactly the right frequency, it changes its energy state. So at the far end of the tube, another magnetic field separates out the atoms that have changed their energy state if the microwave field was as exactly the current frequency. Means we are having the resonance frequency here. So, what we are having at the end of the tube, another magnetic field separates out the atoms that have changed their energy state if the microwave field was at the exactly the correct frequency, that the resonance. So, the detector at the end of the tube gives an output proportional to the number of the cesium atom striking it, and therefore peaks in output when the microwave frequency is exactly correct. So, resonance condition just here we can satisfy. So, detector can and the tube gives the output proportional to the number of the cesium atoms striking it. Therefore, the peaks in the output when the microwave frequency is exactly the correct, the same. So, this peak is then used to make the slight correction necessarily to bring the crystal oscillation and hence the microwave field exactly on the frequency. So, this log frequency is then divided by 9,192,631,770 to give the familiar 1 pulse per second required by the real world. So, how is the atomic time measure? This is a good question, that how we can measure the atomic time. So, the correct frequency of the particular cesium resonance is now defined by the international agreement, that is defined by this value 9,192,631,770 Hertz. So, that when divided by this number, the output is exactly 1 Hertz or the 1 cycle per second. So, the long term accuracy achievable by the modern cesium atomic clock and is better than 1 second per 1 million year. So, the hydrogen atomic clock shows a better short term accuracy, that is approximately 10 times the accuracy of the cesium atomic clock. So, hydrogen atomic clock works more efficiently. Therefore, the atomic clocks have increased the accuracy of time measurement about 1 million times in comparison with the measurement carried out by means of the astronomical techniques. So, here we are just talking about the cesium clock, we are talking the hydrogen clock. So, how many types of these clocks? So, now we define the types of atomic clock. So, atomic clock types today, though there are the different types of the atomic clock, the principle behind all them remains the same. Means we just satisfy the resonance condition or we measure the transition between the two states. So, the major difference is associated with the element used and the means of detecting when the energy levels changes. So, the various type of atomic clocks include, first one is the cesium atomic clock that employ a beam of cesium atom. So, this clock separates the cesium atom of the different energy levels by the magnetic field. Another is the hydrogen atomic clock that maintain the hydrogen atom at the required energy level in a container with wall of a special material so that the atoms don't lose their higher energy state too quickly. So, another is the hydrogen atomic clock. Third is the rubidium atomic clock. So, this is the simplest and most compact of all. So, use a glass cell of rubidium gas that changes its absorption of light at the optical rubidium frequency when the surrounding microwave frequency is just right. So, most accurate atomic clock available today use the cesium atom and the normal magnetic field and detectors. So, in addition, the cesium atomic cesium atoms are stopped from zipping back and forth by the laser beam, reducing the small changes in the frequency due to the Doppler effect. Means we are not changing the level. It must be insensitive from the external effects. So, to determine a spacecraft distance from the Earth, navigators send a signal to the spacecraft, so which then returns it to the Earth. So, the time the signal requires to make that two-way journey reveals the spacecraft distance from the Earth, because the signal travels at a known speed, that is the speed of light. So, in this manner we can detect the distance of the spacecraft. So, this is the one of the example of the atomic clock and one of the application of the atomic clock that we can elaborate in a very big manner. So, while it may sound complicated, most of us use this concept every day. The grocery store might be a 30 minutes walk from your house. If you know you can walk about a mile in 20 minutes. So, then you can calculate the distance to the store. The similar manner, by sending the multiple signals and taking many measurements over the time, navigators can calculate a spacecraft trajectory, where it is and where it's headed. So, by the space navigation standards, quartz crystal clock are not very stable. So, after only an hour, even the best performing quartz oscillators can be off by a nanosecond. So, after 6 weeks, they may be off by a full millisecond. So, or a distance error of 185 miles. That would have a huge impact on measuring the position of the fast moving spacecraft. So, atomic clock combine a quartz crystal oscillators with an ensemble of the atoms to achieve the greater stability. How we can make it most precisely, and how can make the accurate distance of the spacecraft or the satellite by using the atomic clock, when it will be combined with a quartz crystals oscillators with an ensemble of atoms to achieve greater stability. So, there is a one of the NASA's atomic clock, which is the NASA's Deep Space Atomic Clock, will be off by less than a nanosecond after 4 days and less than a microsecond and after the 10 year. So, this is the equivalent to being off by only 1 second every 10 million years. So, atoms are composed of a nucleus that we all know, surrounded by the electrons. So, each element on the periodic table represent an atom with a certain number of the protons in its nucleus. The number of electrons around the nucleus can vary, but they must occupy the discrete energy levels or the orbit. So, energy required to make electrons change orbit is unique in each element and consistent throughout the universe for all the atoms of a given element. So, for instance, frequency necessary to make electrons in a certain carbon atom change every energy level is the same for every carbon atom in the universe. So, the deep space atomic clock uses the mercury atom. So, a different frequency is necessary to make those electrons change level, and that frequency will be consistent for all the mercury atom. So, the fact that the energy difference between those orbits is such a precise and stable value is really the key ingredient for the atomic clock. Further, we will discuss in the next lecture regarding the atomic clock, and then we will use its utilization. Thank you very much.